Welcome back. One more section. So we've talked about how earthquakes occur, seismic waves, what they've helped us figure out, the hazards associated with earthquakes. So how do we measure them? This is something we will spend some time in lab doing and talking about. So there are a number of different ways to measure them. We'll kind of focus on two. So the first is the modified Mercalli intensity scale. This measures the maximum intensity of shaking at a location. So this is specific to a location. Some other ways to measure earthquakes is just to give it one value overall. This really kind of targets what each person feels in a different area. So when an earthquake occurs, it could occur and be felt over a number of different areas through a bunch of different cities. Well, how someone in city A who's further away feels that earthquake is going to be quite different than someone in city B that may be at the epicenter of the earthquake. This scale kind of accounts for all of that. Because obviously the shaking from an earthquake varies from place to place. The further you get out, the less shaking. So does the intensity scale. So what's neat about this one is that this scale is just based on descriptions of what people feel, see, and the damage that occurs around them. So it's really a great and easy way for people and scientists to put a quick value on how intense the shaking was at a particular area. As you get further away from the epicenter of the earthquake, that's the point on the surface of the earth directly above the focus where the earthquake actually occurs. It's measured using Roman numerals from 1 to 12. But again, and it's based on a set list of things that if you see or feel, it might be one thing on the scale, or if you see or feel something else, you just kind of check where that is on the scale and it gives you a certain value. Again, this really is more meaningful to the non-scientist because it's talking about what you feel, what you see, the damage occurring. Some other measurement tools of earthquakes that we use are very sciencey, very math-driven, very numerical-driven, and it doesn't really tell us what damage occurs. It just kind of gives us a number. So this is the modified Mercalli scale. Looking at maybe a 2 on the scale, which is very weak. This might be hard for you to see, so I'll read it. Maybe it's only felt by a few people at best, especially on the upper floors of a building. Delicately suspended objects may swing. So maybe if you're in your kitchen, in your dining room, and you have like a hanging lamp and you kind of see it swaying back and forth, well, that would be a 2 on the Mercalli scale. We feel earthquakes here in the Phoenix area all the time. A couple of years back, there was an earthquake, I believe, down in Mexico, and I got up to get something out of the kitchen, and I have a few hanging things. I have like a fruit basket where I keep all my fruits and vegetables, and there's a couple of wind chimes inside. I don't know, they just look cool. Anyway, I went and got up to get something from the kitchen, and those things hanging from the ceiling were kind of just gently swaying back and forth. And me, being a geologist, you know what my first thought was? Ghosts. No joke. I was like, oh man, we got ghosts. And I laid back down on the couch. And then about an hour later, I was on the computer, on the news popped up, earthquake felt in Phoenix. And I go, oh, yeah, because I'm a geologist. I get it. So in any case, hey, even scientists make mistakes, I guess. So, but again, this scale is based on what you see, what you feel. As you get further down the scale, for instance, destructive, that's number 8, Roman numeral 8. Damage slight in specially designed structures, considerable in ordinary substantial buildings with partial collapse. Damage great in poorly built structures, fall of chimneys, factory smokestacks, columns, monuments, walls, heavy furniture is moved. So based on the damage and what you see and feel going on around you, you can assign it a scale on this, or assign it a value on this intensity scale. So again, very great for the non-scientist. There's nothing necessarily you need to measure. It's just what do you see, what do you feel. That's different than the Richter magnitude scale. This is the scale that you'll hear on the news or you'll see in movies. In Los Angeles today, there was a magnitude 7 earthquake, shook the ground. They're talking about the Richter magnitude scale. Not an intensity scale, but a magnitude scale. This is a measurement of the total amount of energy released in an earthquake. And it's related to the area of the fault on which it occurs. The larger the area of the fault where there's breakage and slippage, the larger the earthquake, because there's more movement, therefore more energy is released. The Richter magnitude scale is based on, that's the paper with the scribbles on it. That's used to help measure the Richter magnitude scale. So you take those scribbles, which are looking at S waves and P waves, and you're looking at heights of these scribbles over these waves, amplitudes, differences in time. Again, it's a very numerical, mathematical, scientific way of just assigning one value to an earthquake, saying how much energy was released. Now, the bigger the earthquake, the bigger the Richter magnitude scale, so the higher that number goes, the bigger the earthquake is. However, if that earthquake happens in the middle of nowhere where no one lives, well, there's not going to be much damage. But if it happens underneath San Francisco, there's going to be a lot of damage. So it doesn't really tell you how much damage was occurred or what kind of damage occurred. It just tells you how much energy was released. It's on a logarithmic scale. So again, it's going to get kind of mathy here. So let me tell you what kind of a logarithmic scale is. So if you're comparing a magnitude 7 earthquake versus a magnitude 8 earthquake, from one step up, 7 to 8, there's 10 times more movement and 32 times more energy released by going just that one step. If you go 2 steps, let me move me probably real quick. If you go 2 steps, it's 10 times 10. It's multiplicative. It's not additive. So there's 100 times more movement. And as far as energy, 32 times 32, that's 1,024 times more energy. That's what logarithmic means. Each step up isn't additive, it's multiplicative. So it gets bigger and bigger and bigger and bigger. It's almost exponential. So looking at this chart, which just looks at the earthquake frequency versus the magnitude, each year worldwide, as far as like magnitude 2 earthquakes, there's 1 million. 100,000 3, 12,000 4, 2,000 out of 5, 200 out of 6. So as you start to get, past 5, you're starting to get into some destructive stuff. So even a 5, lighter earthquakes, some property damage, but now you're getting some property damage in the billions, major earthquakes, great earthquakes. So when you get a magnitude 8, typically there's about three of those a year on average. 9 or above, there's less than 1 a year. So 9 or above are actually kind of rare. There's earthquakes all the time. They're mostly small. Big ones, very rare. Thankfully. So what we do to figure out the magnitude of an earthquake is use what's called a nomogram, this thing. So we look at some of this information. This is a seismograph as taken from, this is a seismogram as taken from a seismograph. These are the scribbles. So we can look at how far away this machine was from the epicenter of the earthquake, which is distance. We can take the difference in time from when the S wave occurred and the P wave occurred. Remember, P waves travel faster, so they get there first. Oops, excuse me. S waves are slower, so they get there second. We can look at the amplitude of this scribble. That's measuring the highest peak of this scribble on that piece of paper. And we can use all that information to then figure out the magnitude. So let's take a look. So let's look at the S minus P time. So it looks like the S wave starts right around here, which looks to be right around 4 seconds. That's right about when things start to get big, so about 24 seconds. The P wave arrived, it looks like, at time 0. Nice for us. So 24, so S minus P, 24 seconds minus 0, excuse me, minus 0 seconds. Wow. 24 minus 0 gives us 24 seconds on this S minus P scale. So right around there. And then I want to measure the magnitude of the highest peak of these scribbles, which is going to be in the S wave since they are more destructive. So it looks like in this example, it's telling us this one is the highest peak. So if we were to measure this on this paper, so this line is 0, so it looks like 21 to looks like 23 millimeters amplitude, which would put us right around in this section. And then from there, we just draw a straight line from this point to down to this point, and wherever that line crosses the center scale of magnitude, that gives us the Richter magnitude. So based on just this seismogram from the seismograph, using this nomogram, we can figure out that this tells us that the earthquake had a magnitude on the Richter scale of about 5, maybe 5.1, somewhere in there. But again, that doesn't tell us how much damage was done, what occurred. It just is a number on a scale based on some measurements to tell us how much energy is released. So that's why the Richter magnitude scale is kind of meaningless to the non-scientist. So on the news, when they're talking about, oh, it was a magnitude 5 earthquake. Okay, well, what does that mean? What happened? What occurred? That's not what this scale is. The modified Mercalli scale does tell us those sort of things. So that's why it's kind of more important to the non-scientists. So what are some of the largest earthquakes ever recorded? All right, so I want you to kind of look at where all of the largest earthquakes, at least in the recorded history, have been recorded. All right, look at them. They're all kind of in this area. There's none over here. There's none over here. All of the largest earthquakes that have ever occurred that have been recorded, all in this area. They're all around the Pacific Ocean and the Pacific Plate. All around here. A large area around the Pacific Plate and some of the surrounding plates are convergent boundaries or subduction zones, which can cause very, very, very large earthquakes. There are convergent boundaries other places in the world, but for some reason, right around the Pacific Plate and some of its surrounding plates, we get some of the biggest movement, therefore the biggest earthquakes. The largest earthquake ever recorded, 1960 in Chile, a 9.5 magnitude earthquake. So the largest in the United States happened up in Alaska at 64, 9.2. We will look at in the assignment the earthquake that happened in Japan in 2011, which was a 9.0, which is a big, big, big earthquake. So these are big earthquakes, but you can see in recorded history, there's only been 1, 2, 3, 4, 5 magnitude 9 or above earthquakes in recorded history, and that only goes back, about 100 years or so. Once we have the tools to measure it. All right, let me put me back here. So what's the maximum magnitude on the Richter scale? It's actually open-ended, meaning there's no kind of limit on how large an earthquake could be. But again, we've only measured up to a 9.5. It doesn't stop at 10 or 12 like the modified Mercalli scale does. It's just kind of open-ended. However, there is a limit just based on the size of the earthquake. For example, a magnitude 12 earthquake on the Richter scale would require a fault larger than the Earth itself. So unless the whole Earth rips apart, you're not going to get up that high. Here's a cool website that you can go to that kind of has some great information on earthquakes. It's the USGS, U.S. Geological Survey Earthquake Hazards Program. Let me jump to that right now. What's cool about this, you can actually check out some of the latest earthquakes in real time. So let's see here. In the past day, magnitude 2.5 or above, there was a 5.1 in China, 4.8 in China. There was one in Nevada, a 2.6. There's one in, looks like just north of San Francisco, magnitude 3.6. But on the Mercalli scale, it was like a 4. And you can see how deep below the Earth the focus was. Hell, there was even one in Oklahoma. Look at that. All right, fun stuff. These are some hot jams I want you to listen to. You got it? Listen to these hot jams. So what are some of those big or main ideas as it pertains to earthquakes? Some of the basics and locations in the U.S. and around Arizona. The different types of faults, normal, reverse, strike, slip, and how to identify those. Primary versus secondary hazards, what those mean, some examples of those. And the waves, the different types, body wave, surface wave, focus more on the body waves, S and P waves, and how those waves kind of helped us figure out what's on the Earth's interior. As far as the scales are concerned, we will look at those in lab. With that being said, let's wrap it up. Until next time, I'll see you then. Bye-bye.